Well, hello. I hope you're having a great day so far. We're going to dive in and talk about graphing factored polynomials. And I wish you could see the scene here while I'm making this video. I've got a little Mackenzie next to me, and I'm just kind of holding my breath that she'll sleep a little, at least long enough that we can get this video in. Otherwise, I'll be in and out, but we'll put it together, piece it together one way or another. So our goal tonight is to be able to graph this function right here without using our calculator. So somehow, by the end of the video, we're going to be able to come up with this function here, and we're going to use everything we've learned up to this point about factoring and finding zeros, as well as analyzing the end behavior. Remember from our last video we talked about this is a 7th degree polynomial, and because it's odd, it's going to start low, end high, especially having that positive leading coefficient. And we're also going to teach you how to make a sign chart, which is going to help us determine when the graph is above the x-axis, like it is between -2 and -1, as well as between 0 and 1 it's above, and then again from 2 all the way to infinity. So you're thinking to yourself, this seems very overwhelming right now. How in God's green earth are we going to be able to graph these polynomials without our calculator? And step one is going to be very simple. We're going to just factor the polynomial. And every once in a while, we're going to get really lucky tonight, and they're going to be factored for us already. Either way, once we get it factored, we're just going to tee it up and find the zeros. Then we're going to determine the end behavior by analyzing what? By analyzing the degree of the function and whether the leading coefficient is positive or negative. Okay, and then here comes the zinger. This is the new one, and if you're going to put a star next to anything, we'll star step number 3. We're going to make what's called a sign chart. Okay, and it's a fun little gizmo that's going to really help us determine what parts of the graph are above the x-axis versus what parts are below the x-axis. Okay. So now let's focus on how in the world we're going to determine when the graph is above versus when it is below the x-axis. So here's what I'm thinking. For instance, let's pick a point here. Maybe I'm going to pick -1.5. So I want to evaluate f of -1.5. Notice the x coordinate is right here. So we're going to go straight up, and oh my goodness, looks like I'm hitting, maybe the y value is about 10. Now here's what we're saying. I would say that f of -1.5 is greater than 0, because the answer was a positive 10. And anything that's greater than 0, anything that's positive, that means the graph is above the x-axis. Compare that to, let's pick another point. Let's pick, actually let's go with 1.5. If I was to evaluate f of 1.5, looks like I'm right here, looks like about -10. But today we're not so much worried about the 10. What we're going to say today is that f of 1.5 is less than 0, aka it's a negative, has a negative value. And anytime we say negative, what we're really saying is that the graph lies below the x-axis. So let's see if we can kind of summarize this. And we'll say if f of some random number called a is greater than 0, aka it's positive, then f of x lies above the x-axis. However, if f of some random number a is less than 0, aka it's negative, then f of x lies below the x-axis. So we're really just focusing on a positive and negative, and that means above and below. So you're probably wondering, what in the world does a sign chart look like? And what it looks like is a gigantic number line. And I'm going to put the 5 zeros that this function has on this gigantic number line. I'm going to spread them out a little bit. And what you'll notice is, first of all, would you agree that this section of the graph is below the x-axis? So what I'm saying, when we're below the x-axis, I'm going to say that every value between -infinity and -2 is negative. Okay? Next thing, we'll say, do you agree that everything between -2 and -1 is above the x-axis? So I'm going to put a series of plus signs there, and that represents above. And that's not saying not just one value, but every single value between -2 and -1 is above. And then we'll say, well, we got this little bump in the road here that's below, so I'll put a bunch of negatives. then I'm above the x-axis, so I'll put a bunch of positives. And then we're below the x-axis again, so I'll put a series of negatives. And then last but not least, everything from x equals 2 to x equals infinity is above the x-axis. So that's what a sign chart looks like. Okay, we just saw how to make a sign chart if we already have the graph in front of us, but usually it's going to be just the opposite. We're going to have to make our sign chart by using this equation, and then we can use the sign chart to help us draw the graph last, okay? So drawing the graph is the end result. In order to get that done, I'm going to set my factored polynomial equal to 0, and I'm going to tee it up. And as I do that, I end up getting zeros of x equals 0, x equals negative 2, and x equals negative 5. And those are my three x-intercepts. Now hypothetically, if you tried to draw the graph right now without making your sign chart, you got your x-axis, you got your y-axis, and you can say here's negative 5, here's negative 2, and here's 0, right? Those are my three x-intercepts. We really don't know what the graph's going to do. Maybe the graph comes down and then up and then comes down. Or maybe the graph does one of these things. And you're thinking, well, I know what it's going to do because I learned how to, analyze the degree of the function and to study the leading coefficient, all that jazz. But then sometimes the graphs do real sneaky things. Like sometimes the graphs, they'll come down, and what they'll do is they'll go up and they'll bounce off of the 0, and they'll come back and cross later. Or maybe it'll come up, it'll bounce, and then it'll cross later. And so this idea of bouncing, where it touches the x-intercept but then bounces back up instead of crossing the x-axis, is a very sneaky thing that these graphs do once in a while. And the sign chart is going to help us catch that. So let's go ahead and we'll make our first sign chart. And on this giant number line, we're going to write down our three x-intercepts, negative 5, negative 2, and 0. And what you'll see here is 4 different intervals. The first interval starts at negative infinity and extends all the way to negative 5. The second interval starts at negative 5, extends all the way to negative 2. The third interval starts at negative 2 and extends all the way to 0. And I think you get the point. The fourth interval starts at 0 and extends all the way to infinity. And to make my sign chart, I need to test all 4 intervals. The first interval, you have the freedom to pick any number between negative infinity and negative 5. Really, any number. It doesn't even have to be the same number that I pick. Now, within that interval, my favorite number is negative 6. So I'm going to go ahead and I'm going to substitute that into the original equation. And I don't have it on my screen, but you have it on your paper there. So I think it's negative 6 plus 2 squared times negative 6 plus 5. And what you have here is a negative number times, in the first set of parentheses, you get negative 4 squared, which turns out to be positive 16. And in the next set, negative 6 plus 5 is negative 1. And if you multiply a negative times a positive times a negative, you end up getting a positive answer. Okay? And that tells me the graph lies above the x-axis throughout the entire interval, negative infinity to negative 5. Now the next interval, you have the freedom to pick any number between negative 5 and negative 2. It doesn't even have to be the same number I pick. I'm going to pick a negative 3 and I'm going to substitute it into the original equation that was factored for me already. And I've got a negative number times, let's see, I'm getting negative 1 squared, which is positive. And then over here I'm getting, oops, that should be a 5 right there, shouldn't it? Negative 3 plus 5 is a positive number. And if we multiply a negative times a positive, we get a negative answer, which tells me that graph lies below the x-axis between negative 5 and negative 2. All right, let's see if we can grab another color. I'm going to pick a negative 1, and I'm going to plug it into the original. Negative 1 plus 2 squared times negative 1 plus 5. And that gives me a negative times a positive times a positive. Oh my gosh, look at this. A negative times a positive ends up being a negative. Look at that. The graph stayed below. Do you see that? This is what's happening. Something really crazy is happening. The graph is going to bounce. And let's make a note to ourselves right there. It's going to stay below after it touches negative 2. And I'll show you what that looks like here in a second after we graph it. Let's get one more color here. All right, for the last interval, I'm going to pick a positive one. I'm going to substitute it into the original equation. 1 plus 5. And what I'm getting is a positive 1 times a positive 9 times a positive 6. And if I multiply three positives, I get a positive answer. So the graph lies above the x-axis. So let's see what this looks like if I graph it. Okay. Here's my x-axis, here's my y-axis, and we said we've got roots of, we'll say there's -5, there's -2, and there's 0. Here's what this graph is going to look like. It's going to start above, it's going to cross at -5, it's going to stay below until it touches at -2. And then here's what happens. It doesn't cross over the x-axis, it bounces and turns back around before it actually crosses at 0 and goes above. So here's a great looking picture of what f of x might look like without using our calculator. So here's a really challenging, interesting question for us. What's the largest number of x-intercepts, or zeros, that a polynomial could possibly have? And what I've done is I've wrote out 6 examples for us to investigate and eventually form a hypothesis or a prediction about what the answer might be. Now in this first function, f of x, if we multiplied x times x, we'd end up with x squared. So it's a second degree polynomial, and you'll notice it has 2 zeros, or 2 x-intercepts. So I'm going to put z equals 2 for zeros. G of x, if we multiplied x times x times x, we'd end up with x cubed. So the degree is 3. It's an odd degree function. Or I should say, yeah, odd degree. And you'll notice that there are exactly 3 zeros. So z equals 3. For our next function, h, or x times x times x times another x, is x to the 4th. So this is a 4th degree polynomial. And there are exactly 4 zeros. So z equals 4. So far, after 3 examples, my hypothesis might be, well, the number of zeros is equal to the degree. Number of zeros equals the degree. Number of zeros equals the degree. Now let's see if that hypothesis holds water as we tackle these next 3 examples. This first function, r of x, is a second degree. That's an x squared. And you'll notice there are no roots. This parabola never crosses the x-axis, so there's 0 zeros. The next function, x squared times x, is x cubed, so it's a third degree polynomial with exactly 1 zero. Very interesting. X times x times x times x is x to the 4th, so I'm going to call this a 4th degree polynomial, and there is exactly 2 zeros. So my original hypothesis was disproved by these 3 examples with a green marker, and so here's what I'm going to give you. The largest number possible for the x-intercepts is equal to the degree of the polynomial. Now notice I didn't say that the exact number of x-intercepts is always equal to the degree. I just said the largest possible number of x-intercepts is equal to the degree. Many times though, the polynomial has less than the maximum number. So for instance, if I had a 5th degree polynomial, the most x-intercepts I could possibly have is 5 or less, but I'll never have more than 5. Here's another similar question. What's the largest number of turning points that a polynomial can have? First of all, what are turning points? Turning points are a combination of relative maximums and relative minimums. Okay, and we got a really nice picture here to just remind us in case we forgot what a relative max or a relative minimum was. And those added, the number of relative maximums plus the number of relative minimums equal the number of turning points that a function has. Of course, a relative max is any point where the graph changes from increasing and then it turns to decreasing, or if it changes from decreasing to increasing, now we call that a relative min down there. So what is the largest number? Well, believe it or not, and this graph right here might tell you the answer. Anybody know what degree this is? Yeah, this is a 3rd degree polynomial, and it's got 2 turning points. And that is true to our pattern. The largest possible number of turning points is 1 less than the polynomial's degree. So let's see if we could generalize that. If my polynomial had a degree of 6, the largest number of turning points, we'll say TP, equals 5. Now that doesn't guarantee it's going to have exactly 5. We're just saying it's at most 5. It might be 4 or 3 or 2 or 1. If I had a degree of 10, a 10th degree polynomial, the largest number of turning points I could possibly have is 9. Here's a mega problem for us to sink our teeth into. They want me to graph this function f of x equals x cubed plus x squared minus 4x minus 4 by finding the zeros and determining the sign of the function between the zeros. And that's our lingo right there, that is they're directing us to make a sign chart to determine when the graph is above versus below the x-axis. Now, first of all, the bad news is this function's not factored. So the first thing I've got to do is factor it. You'll notice there's a grand total of 4 terms. And anytime we recognize a polynomial with 4 terms, we're going to use a technique called factor by grouping. And we're getting better and better at that every single time we do one. So I'm going to start pulling out my GCF. So my first group has a GCF of x squared. And then my last 2 terms there have a GCF of negative 4. Alright, now let's break it down into these groups right here. These 2 groups have something in common. They have a GCF of x plus 1, and as I pull that out, I'm left with x squared minus 4. And just when you thought it was almost over, we noticed we had a difference of 2 perfect squares, and so we had to factor it even some more. Now what I'm going to do is I'm going to set these factored terms equal to 0. As I tee them up, I end up getting zeros of x equals negative 1, x equals negative 2, and x equals positive 2. So going back to the last couple of slides, this was a 3rd degree polynomial, so we knew the largest number of zeros we could have was 3, and exactly we did end up with 3. Okay, now we're going to make a sign chart, which means I'm going to draw a really long number line, and I'm going to put negative 2, negative 1, and positive 2 on that number line. So my zeros always go on the number line. And one of the things I'm going to do is, so we've got 4 intervals. The first interval starts at negative infinity, extends all the way to negative 2. The second interval starts at negative 2, extends all the way to negative 1. The third interval starts at negative 1, extends to 2. And the fourth interval starts at 2, extends all the way to infinity. And I'm going to test each interval. For the first one, I'm going to use negative 3 as my test point. What I'm going to do is I'm going to plug it back into the factored form. And I think that's worth making a very special note in our notebook, is that we're going to substitute our test points into the factored form of the equation. As opposed to what, you're saying? What were my other options? Well, your other option was the original equation itself, and which means I could have plugged it in right up here. And you certainly could, and you'd get the same result, but I think it's going to be a lot easier mentally to do our number crunching if we plug into the factored form right here. So here's what happens if I substitute my negative 3. I get negative 3 plus 1 times negative 3 plus 2 times negative 3 minus 2. And so what I get here is I've got a negative 2 times a negative 1 times a negative 5. Now notice all I did is I wrote down my negatives. I could care less actually what the numbers were. I just need to know what's a negative times another negative. And that equals one big gigantic negative. So that graph is below the x-axis between negative infinity and negative 2. My next test point is going to be negative 1.5. And I'm going to plug it into the original function up here. And that's going to give me negative 1.5 plus 1. Negative 1.5 plus 2, and negative 1.5 minus 2. And so I'm getting a negative times a positive times another negative, and I'm going to say that a negative times a negative equals a positive. So this graph is above the x-axis between negative 2 and negative 1. My next test point is going to be a 0, my favorite number in the whole wide world. And because it's the easiest number to evaluate. So I got 0 plus 1, 0 plus 2, and I've got 0 minus 2, which means I've really got a positive number times a negative number, which equals a negative number. So this graph lies below the x-axis between x equals negative 1 and x equals 2. The fourth interval, I'm going to use a 3 as my test point, and I substitute it, and I get 3 plus 1 times 3 plus 2 times 3 minus 2. I've got a positive times a positive times a positive, and that's probably the easiest one to calculate. That equals one big positive, so we're above the x-axis. Notice there's not going to be any bouncing on this one because we alternated from below to above to below to above, and so we're literally going to cross over the x-axis. And let's see if we can put it all together. We'll draw my x-axis, we'll draw my y-axis, and I'm going to label, let's say that's -2, that's -1, and here's +2. We're going to start off below the x-axis, and then we're going to cross at -2. We're going to cross at -1. We'll cross again at 2, and then we're going to stay above the x-axis the entire time all the way to infinity, and that's exactly what f of x is going to look like without using my calculator. Well, here's another mega problem for us to sink our teeth into, and as I'm doing this problem, I'm really hoping and praying that you can see this problem on your screen right now. This will be the 3,000th time I've tried this video, and every time I post it on YouTube, it comes up as a ghost question, and so I'm really keeping my fingers crossed. But anyway, here's it's at first it was a nightmare because I counted 1, 2, 3, 4, 5 terms. I'm like, oh my gosh, how am I going to factor a polynomial with 5 terms? The good news is we don't have to factor it because they just gave us the zeros. In fact, we haven't really learned any tricks for factoring a polynomial with 5 terms. So the best news is I'm just going to take these zeros and I'm going to automatically throw them on my number line and start cranking my sign chart. So here's -1. Here's +1, here's +3. The only bad news is we just got done writing in our notebook how we want to substitute our test points, like -2. We want to substitute them into the factored form. Well, the bad news is there's no version of the factored form. I've just got to literally use the original equation. And I'm going to substitute it into each of the x's. So it's -2 to the 4th minus 4 times -2 cubed plus 2 times -2 squared plus 4 times -2 minus 3, and I guess we're going to go grab our calculators. I'm going to type the entire thing in as we see it, and as I'm doing that, I ended up getting a positive number, so we're going to say it's greater than 0. We're going to put a sequence or series of plus signs, and we'll make a note to ourselves that f of x is above the x-axis from -infinity to -1. My next test point is going to be a 0, best number in the world. 0 to the 4th minus 4 times 0 cubed plus 2 times 0 squared plus 4 times 0 minus 3. And that gave me -3 as a final answer, which is less than 0. So we got a series of negative signs, and the graph lies below the x-axis. All right, let's grab another color, shall we? I'm going to use +2 as my test point. So now I've got 2 to the 4th minus 4 times 2 cubed. And again, once I get this entirely substituted, I'm just going to pick up my calculator. And we're going to put that little rascal to work. And as I type in all of these numbers, I ended up getting a negative number again. I said, whoa, I got back-to-back negatives. So we're below again, and what that tells me is that we're going to get some bounce action. The polynomial, it's going to touch the x-axis at x equals 1, but then it's going to bounce off. Now compare that, when I was at -1, it was literally going to cross the x-axis because we went from above to below. The last interval I've got to do is the interval between 3 and infinity, and I'll use 4 as my test point. You don't have to use the same number. You could use 5 if you want. So we got 4 to the 4th minus 4 times 4 cubed plus 2 times 4 squared plus 4 times 4 minus 3. I plugged it all in. I got a positive number. Again, I just did it strictly on my calculator. So the graph lies above the x-axis between 3 and infinity. Let's see if we can put it all together and draw a really, really nice graph. So my roots were, or I should say, here's my x-axis, here's my y-axis. Let's say here is -1, here's +1, here's +3. They said we're going to start above. So I'm going to cross the x-axis, and then we're going to touch the x-axis at 1 but bounce off of it, and then curl around and eventually cross at 3. And here's a really, really accurate picture for f of x. Alright, great job hanging in there. We're on our last slide, and this one's going to be the easiest one of the night. Here, ironically, they didn't give me an equation for f of x, but what they did tell me is that -1, 3, and 5 are my zeros. So I'm automatically going to just put them on my sign chart, my number line. And then we got our 5, okay? And here's what they told me. Catch this. They said f of -2. Now remember, -2 is right here. They said that bears negative. How about that? We don't even have to plug it in. And then f of 2 is also negative. And remember, 2 is right here. So this is negative. We're going to get a little bounce action at -1. Then they said f of 4 and f of 6 are positive. 4 is right here, so we're positive. 6 is right here, so that's positive. So we're going to get some bounce action at 5 as well. So let's write this. We're going to bounce at -1. We're going to cross the x-axis at 3, and then we're going to bounce off the x-axis at 5 again. What in the world is this bear going to look like? Let's say here's -1, here's +3, here's +5. Maybe I'll extend the axis there. I'm telling you, this is going to look awesome. We got to start below, so I'm down in here, and what I'm going to do is I'm going to increase, and then I'm going to bounce at -1. I'm going to dip, and then I'm going to cross at 3. I'm going to dip down, I'm going to bounce at 5, and then go back up. And check out this wild graph. How cool is that graph? So we saved you a special treat for the end. Hoping you're feeling pretty good about these sign charts, and I promise they're going to get faster and faster as you do them. But there's no magic shortcuts. We got to put the work in, and once you put the work in, you'll get rewarded, and it'll get easier and easier. Good luck tomorrow. We'll see you.